In this problem, we're told that Billy has done some work on a calculus problem here. He's attempting to graph a rational function. The function itself is not given to us, but some information about the function is, and presumably this is enough information to provide a sketch of what the function must look like. So what we'll do is walk through this information and see how it affects the graph, and see if we can catalog this information on the piece of graph paper that's given. We'll have to do a little bit of work, but mainly we're just going to be copying that information onto the graph. So let's walk through this. He found a horizontal asymptote at y equal 3. So I'll put y equal 3 at about that height there. I may need to adjust this if it doesn't work out right, but that means, since it's a rational function, that the function must approach that level as x goes to positive infinity and as x goes to negative infinity. At this point, I'm not sure if it climbs up to it or falls down onto it, but I do know that my y values need to approach the value 3 as it leaves the graph paper on either side. There are no vertical asymptotes and no holes, so I don't have to worry about those aspects on this graph. The only intercept, I'm told, is the point 0, 0. So this tells me a couple of things. The function needs to go through that point, and nowhere else will it cross the y-axis, and nowhere else will it cross the x-axis. Of course, a function can only cross the y-axis once, but it could, in general, cross the x-axis more than once, but we now know that the only place that it happens is at the origin 0, 0. The derivatives of my function are given, so if I now draw out the sign distribution for the first derivative and the second derivative, I can combine that information into information about the graph, where it's concave up, where it's concave down, where it's increasing and where it's decreasing, and we can put that information on the graph paper. So normally I like to put these down below the graph, but I don't have much room down there. Well, maybe I can squeeze them in right here and right here. So this will be the sign distribution for f prime. This will be the sign distribution for f double prime. My x values on each of these number lines will exactly match the number lines on the graph of the function itself, the x-axis. So to find the values to place on here, first of all, we call those partition values. I will look for places where the first derivative is equal to 0 and where the first derivative does not exist. First thing I notice is that the denominator, actually in both cases here, is never 0. It's never division by 0. And the significance of that, again, is that we won't have any DNEs on our number lines for our sign distributions. I will mainly need to concentrate on the numerator, and it will give me the value 0 at x equals 0 for the first derivative. So at x equals 0 here, I have the value 0. That means horizontal tangent line at this point. So I'm going to put a little dotted line here to remind me that there's a horizontal tangent line at x equals 0. If I check the signs on either side of the 0, which is the only partition value, and in this case that is then a critical value, since 0 is in the domain of the function, I will check and see the signs now to the right are all positive. If you put a positive number into the derivative, you get a positive back out, and they are negative to the left of 0. So everywhere on the left side of 0, this function should be decreasing from left to right, and everywhere to the right of 0, it should be increasing from left to right. So that tells me now that I should be climbing up to this horizontal asymptote on this side, and I need to be decreasing on this side, so it must be decreasing from that horizontal asymptote as well. All right. It also tells me that I now have a local minimum at x equals 0. So this is going to come into here and rise out of here. Drop in, rise out. The second derivative now will be 0 when this quantity is 0. So off to the side here, I need to solve 30 times 5 minus 3x squared equals 0. I really needed to solve a similar problem over here, but I could observe that the only 0 was x equals 0. Here I will do some algebra. Divide both sides by 30. That gives me 5 minus 3x squared has to be 0. And then solving, let's isolate the x squared. I'll push the 3x squared to the other side, divide the 3 off, and use the root to get at the value of x. Now notice there are two values that satisfy this equation: the square root of 5/3 and minus the square root of 5/3. So I'll put a little plus or minus sign out there. That means there's two values where the first derivative, or the second derivative, excuse me, is 0. One's at root 5/3 and the other's at minus root 5/3. So I will now need to plot the points that go along with those and check the signs. Let's check the signs first. To the right of the square root of 5/3, so my x value is larger than the square root of 5/3, this number in here then, when multiplied by 3, will be larger in magnitude than 5. So this difference here will be negative. I'll be getting a negative in the numerator, that's up here, and I will be getting a positive value in the denominator. This square will make it positive. So negative divided by a positive is negative. So out in this region, it's concave down, some portion of the frown. In between minus root 5/3 to root 5/3, if I stick some value into here, any value in that region, then the sign I will get in the numerator will be positive. Think of x equals 0, for example. That's in that interval. I will get a positive number in the numerator and a positive number in the denominator. So in through here, it's concave up everywhere. Alright, so some part of the smile. To the left side of negative root 5/3, again, this quantity up here, once I square it, will become positive, but this difference will be negative. Think of any value you like out here, say negative 1 million. If you place that in there for x, this subtraction would go negative. So the numerator is going to be negative, but the denominator is going to be positive. Negative divided by a positive will be negative. So out in here, it's concave down as well. Now that we've gathered our information about the first two sign distributions, we can translate that up to our graph. All right. I need to have a horizontal asymptote be decreasing and concave down for a while, then decreasing and concave up, and etc. I could read it right across the line here. To break this into manageable pieces, I will split this graph anywhere that a value has come up. So there was a value of importance at 0 and at the two roots. And on this first interval, I need decreasing concave down. So decreasing and concave down. The specific shape out in this region must be something like that. I then need decreasing and concave up. So it must be a shape like this. Then increasing concave up, that's a shape like this. And then increasing concave down, so it must be a shape like this. Now normally if I had the function, I would plot the 2 points at the two inflection points. We can call these inflection points now because we see the signs changing on the second derivative. I don't have that information, and it even notes that. We don't have enough information to plot the y values, so we're asked to pick some reasonable ones for these points. So at root 5/3, what would be reasonable? I need to be increasing on this entire region to the right of 0. I'm at 0 at this end, I'm up at 3 at that end, so this needs to be somewhere in between 0 and 3. Putting it above 3 would not make sense, because then I would need to decrease later on, and I know that doesn't happen. And putting it below 0 would not make sense, because I'd have to